Now, as we've said, once we've got iterative algorithms, it gives us a lot more things we can do than just simple arithmetic. We can repeat that sequence of steps some multiple number of times based on a decision. And this leads to a whole new class of algorithms, a bunch of things that are going to be really valuable to us. One really useful example of an algorithm is what's often called a guess and check method, where we iterate through guessing different answers to a problem we're trying to solve and then checking to see if we've got the right one or not. We've actually seen an example of this earlier on. Where was that? Well, remember when we talked about our declarative definition of square root? We said we had a definition of square root, and if somebody gave us a good guess for a square root of a number, we could use that definition to check it. So if we got a good guess, we could check to see if that guess squared was equal to x, the thing whose root we're trying to find. All we need is a good way to generate guesses. Well, okay, let's think about that. Could we do it? And the answer is sure. And in fact, we're going to do it with a slightly different example. We're going to do it by finding cube roots, just to do something a little different. Same idea would work with square roots. So one way that we could use this idea of generating guesses in order to find, say, the cube root of some number x, let's assume, just to make life a little easier, that x is an integer. So we're trying to find a cube root of a perfect cube. We could try 0 cubed, then 1 cubed, then 2 cubed, then 3 cubed, and keep going until we get to some place where k cubed is bigger than x. Once that's the case, we know we've gone too far, and if we haven't found something, we're done. The nice thing here is that there's only a finite number of cases to try. So we could generate different guesses and see how well we do in terms of finding an answer. Let's take that idea and the idea of iteration and capture it by finding a piece of code or writing a piece of code to do what we'd like. So here's some code that we're going to use. We're going to have our code actually input something that generates or gives us something we're going to try and find the cube root of. We're going to set up an initial variable called answer, which is going to be 0. That's going to be our guess. And what are we going to do? We're going to walk through a loop where we look at answer cubed and see if it's less than x. If it's not, we're going to increase answer. So there's my iterative loop right there. And we're going to keep doing this until we find the first value where answer cubed is greater than or equal to x. So we're going to generate guesses. If answer cubed is less than x, we know that we're not there. So we'll keep doing it until we find the first one where answer cubed is bigger than or equal to x. Once we're there, we can then check. And we check to see, is answer cubed actually what we want? Is answer cubed equal to x? If it's not, we'll say so. And if it is, well, then we'll say, I found the thing that I was looking for. So, using that iterative loop, and now what I'm doing is I'm just walking through generating guesses for the cube root of something until I find an answer that is either close enough or beyond where I want it to be. We can look at this in idle. So here's a piece of code that does it. It's exactly the code that I just set up there. And let's run it. If I actually now run it, it says give me an integer. Oh, let's take 27. And it gives me the right answer. And we know what it did. It started out with 0. 0 cubed was less than 27, so it went to 1, which is less than cubed is less than 27. Went to 2, which cubed is 8, which is still less than 27. Went to 3, which cubed is 27, so it's still less than where we want it to be. Sorry, it's no longer less than where we want it to be, so we could check to see, was it in the right place. Let's try another couple of examples. Again, I'll go back and I'm going to reload this function. It's going to say for a different one, let's try 24. And again, in this case, it keeps generating instances of answers starting at 0 until it gets to the first one that is greater than 24, which was when answer was equal to 3. And since 3 cubed is 27, which is not equal to 24, in this case it says, I don't have what I wanted. All right, so don't sweat the details of finding cube roots. This is a simple little thing, but notice that it does this generate and guess kind of idea. Now, if we look at that code, we can actually observe a couple of things. One of which is, it only works for positive integers. But we could find cube roots of negative numbers. We just know there's going to be a negative version of whatever the cube root of that absolute value would be. So we can actually go back and fix this. And we can do it pretty straightforwardly. Let's go back into our code. And in particular now, just add a couple of things. One is, we're going to look to see whether the thing we're checking for is less than the absolute value of x. And similarly, to check to see whether the thing cubed is equal to the absolute value of x. That's nice, and that's straightforward. All we have to do is, when we're done, come down here and say, once we found the answer for, say, minus 27, we'll turn it into 27, find the cube root of that, which is obviously going to be 3. And at the end, we'll simply put the minus sign back in as we need it. Let's try that out in idle. That's pretty simple. Here's my code. It's exactly what I just showed there. And if we run this, okay, if we do 27, still does the right thing. But if we run it and we give it minus 27, it gives us back minus 3. The reason for showing this is to see that once I've got the idea for an algorithm, I can often generalize it by looking at other cases and then reusing the same body of code for the key computation and adding in pieces around it to get it to do the things I'd like. Okay, now, what are some of the properties of this idea? Well, we've already seen one of them. We said when we've got a loop, we need to have a loop variable that's initialized outside the loop, that changes within the loop, and where the test for termination depends on that variable. When we start thinking about these guess and check kinds of methods, one of the things that's handy is it's often useful to think about what's called a decrementing function. What are the properties of these things? Well, this is a function that maps a set of program variables into an integer. When the loop is entered, that value is non-negative. When the value is less than or equal to 0, the loop's going to terminate. And inside of it, the value decreases every time through the loop. Often this decrementing function is going to measure how much work do we still have left to do. And so, for example, here, the decrementing function we're using is the absolute value of x minus answer cubed. That tells us how far away we are from the place where we would find the solution. And on each stage, that gets smaller and smaller until eventually it gets either equal to 0 or less than 0, and I know that I'm done. Okay, so those are the kinds of things we'll come back to, this idea of thinking about loop characteristics. But since we've written this piece of code, and since we said that it's important to initialize the loop variable outside the loop and to change it inside the loop, let's see what happens if we don't do that. Okay, suppose, for example, we don't initialize the variable inside. So I'm going to do the following. I'm going to go back to my code, and I'm going to remove the answer equals 0 line. So if I go to my code, right over here, I'm simply going to comment that out. Right? So it says, I'm not going to set up answer equal to 0. And now, I'm going to run that. I'm going to save it away. And I need to give it a number. Let's give it, I don't know, we'll give it 27. Oh, goodness. What happened? Well, we hit an error. And in fact, what we see on the screen is the thing that gets printed out. It's called a traceback that shows us where the problem was. It said in that file that I was looking at, in line 4, when I'm trying to evaluate, and line 4 is while answer cubed is less than abs of x, it says, oh, the name answer is not defined. That makes sense. I didn't create an initial value for it, so how can I be looking at answer to change things? So if we don't initialize the variable outside, we get an error. All right, let's go back to our code. Let's remove that answer, and let's make another change. Suppose we actually do initialize the variable, but we don't change the variable inside. So let's remove the answer is equal to answer plus 1 line. So over here in my code, I'm going to comment that out, and just to be able to see what's going on, I'm going to put in here a print statement that says, let me print out answer. And I'm going to make sure I have appropriate spacing here. Let's run this. I need to save it away. Again, I'm going to give it a variable. And let me make sure I give it something in the right window here. So I'll give it 27. Oh, goodness. What's happening? Well, this is now caught in an infinite loop. So in fact, let me stop it by hitting Control-C, which is the command to stop it. And if I go back to my code here, and I know I accidentally typed in a 27 because I was in the wrong window. If I go back to my code here, you can see what's happening, which is inside that while loop, am I ever changing answer, or A and S? The answer is no. So if that variable initial, or that test initially was true, it's going to stay true, and nothing is changing. So with this in mind, I actually have a real problem. I have to basically have some way of getting a change to the test. Without it, I'm caught in the loop forever. So you see that those properties are going to be important. I need to initialize the loop variable. I need to be changing it inside. And of course, I need to be testing some function of it in the actual test to make sure that I want to get through it. So what do we have? This is now a version of a guess and check method. So guess and check methods can work on problems where there's a finite number of possibilities. I'm going to guess different instances of the thing I'm looking for and check them until I see if I find them. And what we just saw here is a particular version of it called exhaustive enumeration. That is, we simply start at one end of the possible range of values and just try each one in turn. We exhaustively walk through all of them until we find a solution to it. And while it sounds like it could be really slow, and at times it can, you can also see for some problems it works just fine. And we just used it to find the cube root of an integer. All right, with that, we can move on to building on top of this idea.